Welcome back, everybody. In this episode, I would like to implement, I would like to make the array list more array listy. Currently, it's a fixed size list with a size of 1000 pointers to strings, but I'm not really sure if that's really what we want. Actually, what we want is we want to have a list that has a small size and that increases the more elements we add to it. So I would like to start with a small list, for example, 5 elements like this. Let's see if this executes. Okay, segmentation fault because it's already an error. And depending on how many elements we add to the list, actually, how many elements we actually add to the list size adapts. And I know this is problematic because here we are defining a structure list and the structure has a fixed size array. And if we add more elements, well, this is not allowed. So what we probably have to do is we have to find out the different types of memory that we have access to in C, and those are stack and heap. And I would like to just see if there's a solution hidden in that knowledge. And why am I getting so many German results? I want to do English. Change to English. Great. Stack versus heap memory allocation. So I feel like we are currently working on the stack. We have the list argument, and then this is part of the stack memory. But if we want to have a dynamic list, we might have to allocate memory on the heap, which is the working memory of the process, as far as I know. But let's have a look at what we can find online. So, memory in C can either be allocated on a stack or a heap. Memory layout of a C program. Let's have a look at that. A typical memory representation of a C program consists of the following sections: text segment, instructions, initialized data segment, uninitialized data segment, heap, and stack. Okay, the uninitialized data segment is for global variables and static variables. The stack area traditionally adjoined to the heap area. The stack area traditionally adjoined to the heap area and grew in the opposite direction. When the stack pointer met the heap pointer, free memory was exhausted. With modern large address spaces and virtual memory techniques, they may be placed almost anywhere, but they still typically grow in opposite directions. Okay, interesting. The stack area contains the program stack, a last in first out structure, typically located in the higher parts of memory. On a standard PC x86 computer architecture, it grows towards address 0. The stack grows toward address 0, okay. Okay, that's interesting. A stack pointer register tracks the top of the stack. It is adjusted each time a value is pushed onto the stack. The set of values pushed for one function calls turn stack frame. Heap is the segment where dynamic memory allocation usually takes place. That sounds like what we want to have, dynamic memory allocation. If the list array size is exceeded, I would like to point it to a new memory location where the old list is copied. And, well, potentially copied. We have to figure out a new solution. Or maybe we just receive a pointer to point to that new dynamic memory. And we assign the next, for example, 10 bytes, 10 strings, whatever, to that segment. The heap area begins at the end of the BSS segment and grows to larger addresses from there. Okay, the heap area is managed by malloc, reallocate, and free. This is, I think, what we need. When to use malloc. When and why to use malloc. Okay. I can't understand when and why it's needed to allocate memory using malloc. Here's my code. I have a struct, a main function. Okay, this is a main function in which a struct is defined. Now I can do two things, student p or student pointer. And okay, why is it needed to allocate memory when I can just use student p? Yeah. Malloc is used for dynamic memory allocation. As said, it is dynamic allocation, which means you allocate the memory at runtime, which is what we need. For example, when you don't know the amount of memory during compile time. One example should clear this. Say you know there will be maximum 20 students, so you can create an array with static 20 elements. Perfect. Your array will be able to hold maximum 20 students. But what if you don't know the number of students? Say the first input is the number of students. It could be 10, 20, 50 or whatever else. Now you will take input n equals the number of students at runtime and allocate that much memory dynamically using malloc. Yes. You use malloc when you need to allocate objects that must exist beyond the lifetime of execution of the current block. Where a copy on return would be expensive as well. Or if you need to allocate memory greater than the size of that stack. I think for my purposes, this is definitely the right thing to do. So let's have a look at malloc documentation. Malloc, defined in header standard library IO. Aha, okay, so we need a new, we need to include already standard library IO. So that's something new in our code. Allocates sized byte of uninitialized storage. So we call the function. It returns a void pointer. What's the return type here? It's void pointer. malloc size t size t. What is size t? Size t is a data type, an unsigned integer type of the result of size of return value. On success returns the pointer to the beginning of the newly allocated memory. Yeah, but why is it void pointer? To avoid a memory leak, the return pointer must be deallocated with free or realloc. Here's an example. Okay, int pointer 1 malloc 4 times size of integer. Well, we can just, well, size of integer. We point to string pointers, which should be integers as well. Okay, I think we got enough to already do something here. And that would be this right here. This is the critical part. Do we still store the information in a fixed size array? No, we don't, probably. We store the information in a pointer to pointers. Like this. C, pointer to pointer. I fear we have to do some refactoring then. Oh, it's still compiled. But this time we did not specify a fixed size. What happens if we just execute the test? It still crashes. Why does it crash? Why does it crash? Do we have an imposed limit somewhere? Did we really save that file? Segmentation fault. Character array. In the test we have to initialize the array, because right now it's just a pointer to a pointer and probably of size 0 or 1. Array. What if we do size of int times 10. Of course, we need to implement or import standardlib.h, standardlib.h. That compiles, and test says corrupted top size, malloc corrupted top size. Why? Malloc corrupted top size. Corrupted top size means that you are corrupting your program's memory in some way by either writing past the bounds. Are we? We're just adding a couple of elements here. 1, 2, 3, 4, 5, 6, 7 elements. What if we increase the size by a lot? Like 1000 again. That works. Okay, that means that we just exhausted the memory. But why? I'm wondering, because we are allocating into the array the size of 10 integers. And my understanding is that each pointer should be the size of an integer. Or am I wrong? What is the size of a pointer? Can we do size of pointer int? Size of pointer in C. I want to malloc some memory to store a pointer. Yeah, just like what we want. Size of character pointer. Character pointer like this. That compiles, and we can allocate that memory. What is the size of a pointer? Let me just print that. Pointer size is d\n, and then size of character pointer. Compile that. Why does it not work? It's a long unsigned integer, and that's the reason. So this would be 32 bits or 64 bits even. Likely 64 bits because this is a 64 bits machine. So we have 64-bit memory addresses. Very nice. I like that. We're definitely learning something here. Okay, so we create a list and we initially allocate some memory for it. I would like to work on the dynamic allocation of that, and just let's return to doing the proper allocation. So the list array will allocate to it memory allocate size of character pointer times, let's just say 1, and then, which screams for an error, and then let's say we do the current end equals 0. Save that. Current end is not defined. Yes, because I need to put a member access here. That compiles, and if we run the test, then it will be corrupted because we are writing too much stuff into that. Well, because we're trying to access unallocated memory. So so here in the add function, we should actually check if we're accessing current memory, unallocated memory. Accessing unallocated memory, question mark. Then do the following. How do we check that? How do we check that? Is there a way to check in hindsight how much memory has been allocated? I'm not sure about that. C, check size of allocated memory. You can't check the amount of allocated space in C or check the size of arrays. You need to save it as a variable explicitly yourself. Okay. Then let's do it differently. How about we change the array list to include another variable, current size, or better, allocated size. And we are setting okay, we can just set the allocated size to 1 for now. I don't like putting 1 in two variable members right here into the array. We define 1, and then in the allocated size we define 1 again, so that is not ideal in my opinion, but let's accept that for now. And here we check if list allocated size is bigger than how much size do we actually consume? We use the end index. Current end plus 1. So we can write into the current end, that is fine, but not in current end plus 1. Let's just put that in parentheses to make sure we are doing the right thing. If the allocated size on the list is bigger than the current end plus, or is smaller than the current end plus 1, then we violate memory, reallocate, and we can now request more memory using malloc size of character pointer. Let's say, let's just request 3 more bytes. Or even just 1. Let's just request just one more byte. Request one more, not one more byte, but one more pointer. Yeah. And then we can return the result, receive a result from here, from the memory allocation. And where do we put that? This is a long unsigned, I think the new memory allocation is a long unsigned int. Size of character times 1. Is it clever to copy the entire array, or should we just request one more space, space for a pointer, memory space, and put that space into the array, the list array? We can't just indefinitely append to this, I think. I think we have to copy the memory. I'm not totally sure about this, but we probably have to copy the entire the memory. So we have to request size of character multiplied by allocated size plus 1. So we increase the memory by 1. And then we say P is equal to that. But that does not work because we first have to copy all the values over. That is the new P. No, wrong. That is the new L, the new address for the lists. Wait. No, the list array has to be set like that. But before we do that, we have to copy all the memory from the list array into some temporary variable. Can we just declare one here? Temp. What temp? Temp what? Character pointer temp is equal to maybe that. Of course not. In function add allocated size undeclared. Why is it undeclared? It's declared here. Ah. Oops. Allocated size is still undeclared in test C. Line 7, it's declared here, but again, I forgot this point this full stop sign before the variable name. So now the compilation should work. Yes. And if we test, we still corrupt the size. Why? We access the array defined in the list. It is a character pointer of pointers, yes. Then we allocate new memory. And then we have to write new memory into that somehow, while for copy from temp to new allocated memory. For let's just create a new counter and then loop until the allocated size, we should increment that, allocated size plus plus. For counter equals 0. I don't like that double statement here. Counter smaller than allocated size, counter plus plus. And here we can allocate new memory. How do we do that? We do, or not allocate new memory, we have to write the values into the newly allocated memory that is already present in here. That is the array pointer. And we set for each element counter, we set temp counter. That should be it. Of course not. Allocated size undeclared. Of course, we have to act on the list. Allocated size is still undeclared, and it's not undeclared anymore because I just forgot to save. And now the execution works. And I would like to actually see, well, no, does it work? Hello world. Let's see what the printouts are. Hello world, how are you? That is the first initialization. Then what do we do then? Then we retrieve certain values. That is fine. And then before removal, hello world, how are you? After removal, hello world, how are you? What do we remove? Remove element number 100. That does not work, of course. But if we remove element number 0, come on, number 0, then yes, world, how are you? And why does that work? Are we already allocating memory dynamically? Yes, we are, because we have started the list with allocated memory of size 1. And here when we are adding memory, we are increasing the allocated memory. And I would like to, if the allocated size has been increased, I would like to printf and just report that log allocated memory increased to, and then just report that for now. I know this makes it hell of a lot more inefficient, but it's for testing purposes. We get no prints. Why do we get no printouts? Why does the code work, but we don't print anything? Can we print F here? Hello. No, that does not print anything as well. Or does not print anything either. So it looks like printouts don't want to happen here. Printf. Hello, I am printing oh, there it is. Ah, okay. It's just printing something at the beginning, and that's why I did not see that. So let's remove that and just do a proper execution. And see what is printed. And here it says log allocated memory increased to 2, 3, 4, 5, 6, 7. So as you can see, we are dynamically allocating new memory and writing into that memory and removing from that memory. We could also extract all that reallocation and copying, or maybe just the copying to a new method, because we certainly need to allocate or reallocate memory to free memory somehow. And how is that done? For example, when removing elements, we should free the memory, because that will stay, well, the memory will be occupied, otherwise and it will leak. So let's have a look at C-free documentation. Free, and it then provide a pointer. Is that it already? So we provide malloc, receive a pointer, and then we free the entire pointer. If p3 reallocate, there's also a reallocate. Oh, had I known that, realloc. That's probably assigning new memory and copying over. Reallocates the given area of memory. Yeah, copying memory area with fixed size. That's probably what we needed, but let's just use malloc and what is calloc? I don't care. Let's just free the memory. How does it track which memory is free? or how much memory is to be freed. It probably just marks that one pointer, the beginning address, the start address, as unallocated. So next time it will just provide that memory when somebody wants to allocate it. Anyways, remove elements. So if we remove an element, we want to do we really want to free memory? I mean, we're probably, if we're allocating hundreds of elements and then removing them, and then we can expect the array list to also, well, contain hundreds of elements again. So is it really necessary to free the memory? And what should be the threshold? For example, if we remove one element, it would make no sense to just copy the entire array over again and free the entire memory. But of course, we could technically do that, but it would make more sense to create steps. For example, we allocate 1,000 memory units, and then once that is surpassed, we allocate more memory, and once these 1,000, these larger units are, well, underpassed, then we free that memory again. But it does not make any sense with just allocating individual spaces here. This was just as an experiment, so I would like to allocate 100 here and say, or maybe let's just say 10. That's still fine for our testing purposes. But in practice, this should be rather in the thousands. And compile that and test. And the printout is going to be, well, it does not print out anything because no new memory is being allocated. But I can introduce a while here and say while oh no, let's not just exhaust memory for no reason. I just wanted to populate this list and really make it very large, but apparently it's already working fine. For testing, I would say we can leave a 3 in here. Maybe 3. So there are steps that we can observe, but we don't need to do loops with thousands of or hundreds of iterations. And here we can see that we can't see that the memory is being updated. Why can't we see that? Here we can see something, but that's not what I would expect. We allocated allocate more memory. We use the allocated size and then allocate +3. Okay, and then of course we have to expand the allocated size by that number, of course, as well. Threshold. So that is the value that is telling us how much memory we allocate, what is the threshold to be surpassed. And now we should get a better printout like this. No, still not. Are we still doing something wrong? Allocated size +3 should be plus threshold. And here, of course, we also have to use the threshold instead of +1. Otherwise, the code will, well, believe the wrong thing. Okay, now the code seems to be behaving weirdly. Allocated, what is happening? If, okay, no, that should be fine. If we surpass the current end by 1, no, that is fine. Then we should allocate more memory plus the threshold. And I would say now the code should be fine, but it isn't. Allocated memory increased to 3, but yeah, but why? It needs to be, huh? Stupid. I need to increment it by the threshold and not just sum it up and then not return anything. So this is now the solution. Quite sure about that. Yes, so we allocate memory and set the value to 3. Then once this value is surpassed, we increase to 6 and then to 9. And that is already great. So we have a dynamically growing array list now. And well, next time we could take care of removing and freeing up memory. But for now, I'm completely happy with that. And this totally surpassed my expectations of what I could do with C today. And so we definitely learned something new. And I definitely learned something new. And if you like this, then please subscribe and leave a like. And I would love to see you next time. Bye-bye.